Good morning. There are times when it is most convenient to measure molecular weight by gel permeation or size exclusion chromatography. I hope everybody knows if I call it GPC or SEC, we're talking about the same thing, right? Because I may switch back and forth. And you're welcome to switch back and forth also in the spirit of inconsistency. But we do this because it's really rapid to measure the molecular weight by GPC. Sometimes we even have an auto sampler on an instrument that you can load up like 100 vials of stuff and it will just load them automatically. You set it and forget it. And then later that day you have all the molecular weights of all the samples that you've made. But how do you get the absolute MN or the absolute MW of the standards? So who's watching the watchers? If the standards have molecular weights that are well known, how do we know that those molecular weights are well known? Well, the MN and MW for the standards have to be determined using somewhat more experimentally difficult or tedious types of experiments. And today's lecture will be devoted to telling you a little bit about those. So we will cover briefly end group assay to give you MN, osmotic pressure to give you MN, light scattering to give you MW, and MALDI-TOF-MS to give you MN. And we're only going to cover these topics in about 10 minutes each, although they are the subject of probably 100 pages in the book. So if I ask you about any of these things on an exam, how do you get MW? Light scattering and perhaps the first thing about it. But we're not going to derive the equations. It's all in the book, but since this is a polymer class, I have to talk about it. But since it's only a 10-week polymer class, I only have 48 minutes to talk about it. Okay. So how are the absolute values of the molecular weights characterized? So how about end group assay? So you know how many molecules you have in the mixture if you know how many end groups there are. And for example, in end group, so you know how many monomers went in, but once the monomers have reacted, it's hard to find them, it's hard to count them in the solution. So what you have to do is you have to be able to count the number of end groups. If you have the number of end groups, you have the number of polymer chains. So for example, if the end group of a step growth polymerization is an acid, like a carboxylic acid, you get out your burettes from high school, literally, and you titrate, and you find out how many moles of base it took to neutralize the acid. The problem with this technique is that if you have 10,000 or 100,000 monomers, huge number of monomers that combine to give you only one end group, then the concentration of end groups at any time is really, really freaking dilute. So you can only do this for low molecular weight stuff, say like 15 kilodaltons and below. So this is a practical for, let's say, less than 15 kilodaltons. And you could do this by, say, by titration. You could do it, say, what if there was an initiator fragment? Or like a terminal acid or base. Or you could also do it in principle spectroscopically. And one key way that gives you quantitative information is by nuclear magnetic resonance. or NMR. And I'm going to offend anyone who took organic chemistry, including me, who has a PhD in organic chemistry, by drawing an NMR spectrum. But the NMR spectrum of a polymer might look like this. And then your end group might be that right there. There won't be loops in an NMR spectrum, but there will be a lot of stuff. And then the actual end group might just be a tiny little peak that barely comes out of the noise. And if it doesn't come out of the noise, then you can't measure it. I mean, it's really more like that. Just kidding. Okay. Another technique, osmotic pressure. So if you've taken organic chemistry and you spent several weeks interpreting NMR spectra, and you see nice, clean peaks and multiplets from small molecules, all bets are off in polymers. The peaks become very broad because you have lots of different magnetic environments, electronic environments in the molecule, and it becomes harder to resolve individual signals. Yeah.
In order to take an NMR of a polymer, would it have to be in solution or like a liquid phase?
You can take a solid state NMR. It's more difficult. Chances are it's going to be in solution. Yeah.
So could you repeat why you need to use low molecular weight things to do nitric acid?
Sure. So the concentration has to be high enough in order to measure it, either by titration or by spectroscopy. If you have a low molecular weight, then you have a higher concentration for a given number of monomers initially, and if you have a higher concentration, it's easier to pick up the signal. Okay, osmotic pressure is the pressure exerted through a semi-permeable membrane between a solution that has a high chemical potential from one that has a low chemical potential. So the chemical potentials equilibrate by pushing solvent from the dilute side toward the concentrated side to try to equalize the concentrations. But because we have pressure due to gravity, there's a limit at which there's a limit of how much pressure can be exerted due to this osmotic, which is ultimately an entropic effect. So the experiment is done like so. Where we have two sides of a container, and this is a solution, and this is a pure solvent, and the solution has high mu, which is chemical potential, and the solvent has low mu, which is chemical potential. So at equilibrium, stuff will move around in order to get the chemical potentials as close as possible. The solution, so solvent molecules will move into the solution and will exert a pressure difference, which is measured by the difference in the heights of these liquid columns of capital P for osmotic pressure. And just to indicate the fact that we have stuff swimming around in this side, I'll shade it. So solvent goes through the membrane in attempt to minimize difference in chemical potential. But at equilibrium, the pressure buildup on this side exactly counteracts the tendency of the solvent molecules to pass through the semi-permeable membrane, and that quantity is called the osmotic pressure. So the pressure buildup exactly counterbalances the tendency of the solvent to flow. And the membrane is permeable only to solvent. So how this experiment is done in practice is that we measure the pressure exerted for a series of concentrations. And what you do is you plot the osmotic pressure over the concentration, and it equals RT over Mn. And this is, the derivation is on page 259. So it equals RT, the ratio of the osmotic pressure over the concentration equals RT over Mn plus RT times a constant B times C for dilute solutions. C is the concentration, Mn is Mn, R is the universal gas constant, T is the temperature, and B is the second virial coefficient, which is a constant that describes the interaction between the solute and the solvent. And as C approaches 0, so pi over C as C goes to 0 equals RT over Mn, which will be the y-intercept of our plot. So these will be experimental data. So this is PMMA in acetone if you're Italian, acetone. And we'll plot pi over c in units of joules per kilogram and concentration in units of grams per liter from 0 to 10 to 20 to 30, and our pi over c in units or in increments of 5, 10, 15, 20, 25. And say we know what the pressure is because we can measure the difference in pressure with a ruler, and we know what the weight of the liquid in the column is, and we know what the concentration is because we've added the material ourselves. And we get some data. And in the lab, you would actually make your fit go through the data points, unlike what I did here on the board. And let's say that this point, the y-intercept, is RT over mn, because that equals pi over c as c goes to 0. And let's just say, because I already did the arithmetic out for this, is 6.6 joules per kilogram. And therefore, mn equals RT over pi over c as c goes to 0 equals 382 kilodaltons. So before I erase end group assay, what this allows us to do, because we know the number of monomers added, or the concentration of monomers, and we divide this by the number of end groups, which is equivalent to the number of chains. This is just Mn. This is just the number average molecular weight. Number of individual units that went into the flask divided by, upon completion of the reaction, the number of end groups, which is the same thing as the number of chains. Yep.
So why do you measure concentration as it goes to 0? Why is it that, this one is 0?
Because just because of the form of this equation as y equals mx plus b. So RT over mn is the y-intercept. Yep.
Was there an applied temperature used in the calculation of your mn here?
Yeah. In this particular case, it was, oh, sorry, that was an important detail. 303 Kelvin, thanks. So while colligative properties like boiling point depression, melting point depression, boiling point elevation, melting point depression, and osmotic pressure are determined by the number of particles in solution. Other phenomena like light scattering are determined by the size of the particles in solution. So if we use a technique like the like light scattering, we can get something about the weight average. There's a question over here.
Just a quick question. So, see the concentration of the solution in the solution chamber.
Yeah. Yeah. So what is scattering? Scattering is the transient polarization and depolarization of electron clouds of matter due to incident radiation. And we can use this technique, and this is all of chapter 8 is about light scattering in the book, and it's 36 pages, and we could spend a month on it if we wanted to, but we're not going to. So there's a lot of detail here that in the interest of expediency we have to skip over, but I just want you to know it's chapter 8, page 289 to 325. So light scattering gives us the weight average molecular weight. And light scattering itself is the absorption and re-emission by transient dipoles and it depends on, for a polymer solution, the concentration, the size, and therefore the weight average molecular weight, and the polarizabilities of the scattering molecules. What's polarizability? Polarizability is the extent to which a dipole can be formed in a molecule in the presence of an electric field. So it describes the strength of the dipole that's induced in an electric field, or by some oscillating EM wave that produces an oscillating dipole. Now, if some electromagnetic radiation strikes some electron cloud, the electron cloud is deflected a little bit, but not fully absorbed. It's just deflected. As it re-equilibrates, it scatters a photon of the same wavelength. That's called elastic scattering. There are inelastic scattering processes like Raman scattering that we're not going to worry about in this class. And what determines the polarizability is determined in large extent to the closeness of the electron clouds in the molecules to the nuclei, and also how strongly they are they're bound. So we talked about Teflon being a not very polarizable medium because fluorine is an electronegative atom and sucks in its electron density very tightly, so it doesn't scatter very well. So how this experiment is done is we have a sample cell We have some detector, which is at a distance r from the sample cell. Then we have an incident beam and a transmitted beam that gives us the exact location of the Ark of the Covenant. And for for small enough particles, so for small particles, and by particles I mean polymer blobs, so really what I'm going to tell you about today is really for low molecular weight stuff. If you want to know about larger molecular weight stuff, it's a lot more complicated, but it's all in the book. And if you're doing this in the lab, there will be a manual. So for small particles, where the radius of gyration is, say, less than about the wavelength of incidence over 20, there is the scattering is isotropic. What do I mean by scattering is isotropic? There's a theta angle here, but for small enough particles, there's no theta dependence. Okay, so we're making our lives easier by considering only smallish particles. So the measured intensity enters into the equation through this equation, Kc over r theta equals 1 over m sub w plus 2bc, where r theta is the Rayleigh ratio, where r theta itself, I'm sorry about these convoluted definitions, by the way, of I sub Ex over I naught, where I sub Ex is the scattered intensity per unit volume. I naught is the incident intensity. And Kc itself has a convoluted definition of 4 pi. This time the pi is just March 14th times n naught squared over dn dc squared over the incident wavelength to the 4th times Avogadro's number. Of course. So lambda is the incident wavelength, Na is Avogadro, N naught is the refractive index of the solvent. And what you do is you, in practice, plot Kc over r theta versus c, and the slope is 2 times the second virial coefficient, and the y-intercept is 1 over m sub w. So we might have experimental data where we're plotting concentration in grams per mil. From 0.002 to 0.01 in units of or in increments of 0.002. And we have Kc over r theta in units of mole per gram. And I'm just going to try to reproduce the plot in the textbook here. And you get a straight line where the slope is 7 times 10 to the minus 4, and the y-intercept is 1 over m sub w equals 5.46 times 10 to the minus 6. For larger polymer particles, you actually have internal scattering, and you actually get an anisotropic scattering pattern so that you get a theta dependence, and we're not going to talk about it here. Yep.
For the Rayleigh ratio, next to scattering density per unit volume, is that R or is that T gamma being squared?
Where?
Right next to IEX. What is
This is r squared. This is the distance to the detector. Okay, one more technique, and then we will be done with new material for Monday's exam. The last technique is called MALDI-TOF-MS, which is matrix-assisted laser desorption ionization time of flight mass spectrometry. And what you do is you put your polymer in a solid, you evaporate your polymer in a solid film on an organic matrix, and you bombard it with a laser, and you blast it apart, and then the fragments become ionized. And the fragments can be accelerated in a magnetic field to a detector. And because they're charged and they're moving through this magnetic field, if you know how strong the magnetic field was, which you know because it's an electromagnet and you can tune the strength of the magnetic field. And you know what current you registered when the fragment struck the detector, then you know what the mass is. And this is on page 35, so actually quite early on in the book. So the matrix, Mr. Anderson, is an organic acid plus the sample. The laser ablates the matrix. That just means busts it up. Ablates the matrix and transfers charge. So this is matrix assisted, just so we keep our acronyms straight. TOF is time of flight. So the charged sample is accelerated. And the time of flight is determined by m/z, which is the mass to charge ratio. And MS is called mass spectrometry. So you get a plot of the number of counts versus the mass to charge ratio. An ideal scenario is when one polymer chain picks up one charge, and the mass to charge ratio is just the mass over the one charge. But typically, because we have some dispersity to the sample, we're not just going to get one peak, we're going to get something like this, where we can, this is basically just a histogram from which we can get the statistics, but in this case, if it's just a symmetric plot, then this is MN up here. So this works best for relatively narrow dispersities. You can imagine that if it's quite a dispersed sample, then your mass spectra will be a mess of stuff that's difficult to deconvolute. And not all polymers are easily charged. So this might not give you the greatest signal. So you'll want groups that are easily ionized. Yep.
Does the charge come from the organic acid?
Yes, the charge comes from the intense heat that's generated at from the organic acid and the polymer ablating. So it can be transferred from the organic acid and potentially other species.